Welcome back. We finish our discussion of electromagnetic radiation by returning to looking at the wave nature of light and how the wave nature of light results in interference and diffraction. So one of the things that we learned in the last unit was that the speed of light changes when the electromagnetic radiation moves through different materials. So the speed of light that we usually think of, 3 times 10 to the 8 meters per second, is the speed of light in a vacuum, and the speed slows down when the light moves through glass or some other transparent material. We also remember that the speed of light can be thought of as the frequency of light times the wavelength. So the frequency is the number of times it oscillates per second, and the wavelength is how far each wave goes. So the wavelength times the frequency gives you how far the wave goes per second. So then the question is, what happens when electromagnetic radiation travels through a material where the index of refraction is not equal to 1? On the question here, this is a quick reminder about what frequency and intensity mean. So the larger the amplitudes, that means the wave goes up and down more, while the frequency is how often the wave oscillates. So if the speed is constant, then the shorter the wavelength, the distance between the peaks, then the larger the frequency. And the longer the wavelength, then the smaller the frequency. Okay, so what happens when light moves through a material with an index of refraction that is not equal to 1? In our picture, the light travels from air, which has an index of refraction of 1, into a new material, let's say glass, and it has a larger index of refraction. Then the light is traveling slower. So what happens is that the frequency stays exactly the same, but the wavelength decreases. So the light oscillates, the same number of times, but the wavelength is smaller because the light is slower. Now notice, this change isn't permanent. When the light leaves the glass and goes back into the air, the wavelength just returns to its value in vacuum. And of course, when it hits your eye, the index of refraction in your vitreous humor is about 1.34. So the wavelength is shifted, although what really matters is the energy of the photon, and that is the same no matter what the wavelength is. Or when the wavelength changes due to a different index of refraction, the energy of the photon remains the same. So, when the electromagnetic radiation moves through the interface, we get a new wavelength. So the wavelength is used this symbol lambda here, so kind of looks like an upside down Y. So the lambda 2, this is the wavelength in the new material, and this is equal to the index of refraction of the first material times the original wavelength, lambda 1, divided by the index of refraction of 2. So in our case, the first material was air, so N1 is 1, so you divide the wavelength by N2 to get the new wavelength. That means the larger the index of refraction, the smaller the wavelength. This should make sense because the larger the index of refraction, the slower the speed of light, so the slower this light, the smaller the wavelength. We can derive this pretty quickly. The speed of light is the wavelength times the frequency, and the index of refraction is 1 times the velocity is equal to the index of refraction of 2 times the velocity of 2. We replace the velocity with the frequency times the wavelength on both sides, and then divide both sides by frequency, since that's the same. That gives us N1 lambda 1 is equal to N2 lambda 2. This formula from before, it's just dividing out the N2 and isolating the lambda 2. The reason that this is important is that the wavelength is important for knowing what kind of interference occurs between two light sources, so we will need to know the wavelength in different materials. Okay, so you have a couple questions to do, and next we're going to start looking at interference. Good luck.